students. Today we are going to discuss a very important topic of definite integral, that is known as application of definite integral to evaluate surface area of revolution. So we are already familiar with the definite integral, how to determine the area bounded by the plane curve, and here we are going to learn how we can determine the area bounded by the arc length, volume and surface area of the region bounded by revolving a curve about a line. Okay, so area, just on a quick revision, you know this area of the plane region. You know that the area bounded by a Cartesian curve y is equal to fx, x-axis between the line x is equal to a and x is equal to b is given by a to b fx dx. Okay, so this you know from the previous class. Here one example also just for your practice. Okay, just to recall your memory what you did in the area in a point form. Then to find the area inside the chordoid, r is equal to a1 plus cosine theta and the circle r is equal to twice theta cosine theta. Then required area is already stated here. So this area you may calculate by taking the suitable formula, that is 0 to pi a square and 1 plus cosine theta whole square d theta minus pi a square 2. Then on calculation you will get this area, required area is pi a square by 2. So this is the previous requirement prior to start this surface of revolution. So surface of revolution, if you know, then you can remember that a surface of revolution is a surface in Euclidean space created by rotating a curve around an axis of rotation. Example of surfaces of revolution generated by a straight line are cylindrical and conical surfaces depending on whether or not the line is parallel to the x-axis. It is also true that a surface of revolution is obtained when a curve is rotated about an axis. We consider two cases revolving about the x-axis and revolving about the y-axis. That is, if you look this figure closely, then you find here the revolving about the x-axis. Here you can say the rotation about the x-axis. This is the curve y is equal to fx within the ordinate x is equal to a and x is equal to b. So this is rotated about the x-axis. Then the surface area is given by a is equal to twice pi a to b fx under root 1 plus f dash x whole square dx. So this is the formula about this case when revolving about the x-axis. Now similarly you can find out if the curve is described by the function x is equal to gy, where the ordinates are c and d, and that is laying between y is laying between c and d, and this is rotated about the x-axis again. Then the area of the surface of revolution is given by twice pi c to dy under root 1 plus g dash y whole square dy. Similarly, you can go for the third case when the parametric coordinates are given. If the x is equal to xt and y is equal to yt are the parametric coordinates, parametric equations with t ranging from, over some interval alpha to beta is rotated about the x-axis. Then the surface area is given by the following integral formula, that is twice pi alpha to beta yt under root x dash t whole square plus y dash t whole square. So this is about those formula with the respect of x and y. Now in the polar form, if the equation is r is equal to r theta form, within the interval alpha theta is equal to alpha to theta is equal to beta is rotated about the polar axis, then the area of the resulting surface is given by the formula, that is twice pi alpha to beta r theta sin theta under root r theta whole square plus r dash theta whole square d theta. So this is the formula in this case. And then if you talk about the revolution of with respect to y-axis, then the function gy, xt and x theta are supposed to be smooth and non-negative on the given interval. Then if the curve y is equal to fx, where x is lying between a and to b, is rotated about the y-axis, then the surface area is given by twice pi a to b x under root 1 plus f dash x whole square dx. So why these formula are important? The segmentation of the formula will tell you under which case you are going to apply which formula. Now, if the curve is described by the function x is equal to gy, this is the function and this is the curve x is equal to gy, where c is the ordinate c and d, where this curve is lying between c and d, means y is lying between c and d, and rotated about the y-axis. So rotation about the y-axis, then the area of the surface of revolution is given by, तो जो area revolute होगा, that will be twice pi c to d gy under root 1 plus g dash y whole square dy. Now, if the curve defined by the parametric equation x is equal to xt and y is equal to y2 here, in this case, with t ranging from some interval alpha to beta in the rotated about the y-axis, then the surface area is given by the integral twice pi alpha to beta xt under root x dash t whole square plus y dash t whole square dt. Now, if the curve defined by the polar equation r is equal to r theta, with theta ranging over some interval alpha to beta, is rotated about the y-axis, then the required formula will be twice pi alpha to beta r theta cosine theta under root r theta whole square plus r dash theta whole square d theta. So now this is only today I have discussed only the formula. In the next PPT we will discuss about the problems. On which formula which type of the problem is based. But for the practice based on the previous article, not for the surface revolution. So these questions you can do for practice and for better understanding of the subject. Find the lateral surface area of a right circular cone with slant height L and base radius R. So this is the article. With this information you can find out the lateral surface area. Find the area of the surface obtained by revolving the asteroid. X is equal to cosine qt, y is equal to sine qt about the x-axis. And some more problem, you find the area bounded by the curve x power 2y3 plus y power 2y3 is equal to a power 2y3. Find the area bounded by the loop of the curve r square is equal to a sine theta. Find the area inside the r is equal to a1 minus cos theta and outside r is equal to a sine theta. Find the area common to the curve r is equal to a1 plus cosine theta and r is equal to a1 minus cosine theta. So these are the problem for your practice, and in the next PPT we will discuss some numericals based on different surface of revolution. Thank you very much. Thank you.